Okay, so now we're going to look at multiplying decimals. Again, we're going to borrow our algorithm from whole numbers and we'll use place value. But something neat comes out because decimals are related to fractions that we have to keep track of the decimal place. And so, for example, if I had 1/10 times 1/10, well, with fractions, when we multiply across the top, we multiply across the denominator, we notice the denominator gets bigger. And so we're going to have to keep the decimal places getting bigger as we multiply. And so to do that, we multiply as if it is a whole number. Then we count the number of decimal places. In all the factors. And our answer has the total number of decimal places of all the factors. So we count up all those decimal places and our answer has to have that. So that might sound weird, but what it's doing is it's keeping track of those denominators that are hidden in the decimal place. So let's look at one here. So if I'm going to take 0.7 and I'm going to multiply it by 0.9. Now from a fraction standpoint, that's 7/10 times 9/10. Now this is not how we do it, I just want to show you what happens. Well, what we get here is we multiply the upstairs, we get 63. We multiply the downstairs, we get 100. Well, 63 hundredths is 0.63 as a decimal. And so it's these denominators that increase that the number of decimal places we'll keep track of. So let's do the algorithm I said. So we multiply this like it's whole numbers. So I'll write it vertically. So I get 9 times 7 is 63. So I carry my 6 and everything else is zeros. And so my answer is 63. Well, how many decimal places did I have? I have 1, 2. So my answer needs 2 decimal places. So I move over 1, 2. And look, we've got the same thing. And it's the fact that the place is equivalent to a denominator for the decimal part that we can just keep track of how many decimal places we have. And our answer will have the same number of decimal places. Let's do some examples here. So if I have, whoops, let me change colors here. Oh, sorry, cleared that out. There we go. Let's do another example here. And we'll do some multiple examples to get used to this. So if I have 15.9 and I'm going to multiply it by 0.62. So I'm going to write this vertically. 15.9. Now we don't need to line up the decimal places when we're multiplying. So I'll just put 0.62 like this. And we'll use our algorithm for multiplying. 2 times 9 is 8. Carry my 1. 2 times 5 is 10. Plus the 1 is 11. Carry the other 1. 2 times 1 is 2. Plus the 1 is 3. So I've worked on my first number. Now I'll work on my next number. 6 times 9 is 54. Carry my 5. 6 times 5 is 30. Plus the 5, 35. Carry my 3. 6 times 1 is 6, plus the 3, 9. And I'll add up. And now I need to add the decimal places. So I have 1, 2, 3 decimal places. So I come over 1, 2, 3. And I get 9.858, or 9 and 858 thousandths. Again, we're going to just keep doing some examples using the algorithm. So if I have 648 thousandths times 5 tenths. So again, I'll line these up vertically. I shouldn't say line them up vertically, I'll place them vertically. I'm not lining up the decimal place. I really only have one digit down here, so that's going to multiply. Zeros don't do anything for our multiplications. So 5 times 8 is 40, carry my 4. 5 times 4 is 20, 4, carry my 2. 5 times 6 is 30, 32. And now I count my decimal places. 1, 2, 3, 4. So 1, 2, 3, 4. And I have 4 decimal places. All right. There are some patterns that occur with the powers of 10 from this. So notice if I'm going to multiply this by a power of 10, so 100, what 100 is going to say is I'm going to want to move my decimal place over. Well, 100 is 10 to the second, so 2 decimal places. So I can go, so let's just do this as a motion of decimal places. So I'll write what I have, and I'll move over 2 to the right. 1, 2. And so my answer is going to be 50. Now if we think of this in fractional forms, that makes sense. A half times 100, half of 100 is 50. So our decimal is doing the job that we want. And so if the power of 10 is large, we move the decimal place to the right. But if our power of 10 is small, well, we're going to move our decimal place in the opposite direction. So I'm going to multiply 1 to 0.06, but now I have to move my decimal place. Well, this is 10 to the negative 2, right? Hundredths place. So I move my decimal place to the left. Small powers of 10, the negative ones, the fractional part, move my decimal place to the left. So I'm going to go 1, 2 to the left, and I have to fill in the zeros. So 6 hundredths times 1 hundredth is 6 10,000ths. Well, if we look at the fraction, 6 hundredths times 1 hundredth, that's going to give me 10,000 on the bottom and 6 upstairs, which agrees with this. Let's do a couple more of these where we'll use powers of 10. So let's look at large number multiplication. If I multiply this by 10, that means I'm going to move the decimal place 1 to the right. And so this equals 765.43, because I moved the decimal place 1 to the right. If I take the same number and I multiply it by 100, I have 2 zeros, so I multiply the 1, 2. So 765.4.3, because the 2 zeros said I move the decimal place twice to the right. And let's do a similar thing with fractional. or small powers of 10. So we're going to multiply this by 1/100th. So that's 2 decimal places over. So I'm going to move 2 decimal places to the left. So 1, 2, well, I have to add an extra 0. 0, 8, 5, 7, because I moved 1, 2 over. I have to add those extra zeros when moving to the right. Or to the left, sorry. My other right. All right, a place where we're going to see decimals come up a lot, we'll have to do with our friend the circle. And so there's a circle. Now, when we were working earlier, we had talked about perimeter, which when we had a polygon, some object of straight lines, we could add up the length of all the sides to get the perimeter. It would be how much it would take to walk around the edge. So the perimeter of a polygon was for this polygon would be 1, 2, 3, 5, 7, 10, 14. So this perimeter is 14, whatever our units are. But a circle, we don't have straight lines to walk around. And the ancient Greeks studied this, and they found that there is a ratio of, they originally looked at the diameter, but we like to talk about the radius, because the radius is how you make a circle. So if I go from the center of the circle out to its edge, the radius will be the same. Radius is really the distance from the center to any point on the circle. We make circles by pinning a piece of string and holding it taut, and we could trace it out. And so this outer part of a circle isn't called a perimeter. It's called the circumference, due to the fact that it's curved. It gets a special name. And so we're going to have 2 ways to talk about circumference. And they'll use 2 pieces of the circle. We can either have the radius, which has my letter R here, which is the distance from the center of a circle to the edge. Or the diameter, which is the distance from 2 sides of a circle passing through the center. And the diameter is how wide the circle is going to be. When I do work with physics or anything where we manufacture or work with things that are circular, the radius is how we build it. It's easy to build things with the radius because you pin in the center and you rotate. But when you go to measure, you have to cut it to get to the radius. So the diameter is the widest a circle will be. It's always the same width passing through. And so we can calculate the circumference in 2 different ways, because one of the things we note, if this is from the center to the edge, well, that's the halfway point. And so we can say that 2 times the radius is equal to diameter, if I use my variables. Now, the Greeks studied this a lot, and what they ended up doing is they said that the circumference, which I'll use the letter C for, is equal to 2 times a special number called pi times the radius. Or it's pi times the diameter. Now pi, the Greeks approximated to 22/7. But it's really a never-ending decimal. It's like there's certain numbers that we can't write as fractions, and so their decimals go on forever. It's approximately, to 2 decimal places, 3.14. And this is a very useful number. It's written in different texts. I think in the description of King Solomon's temple in the Bible, they actually talk about, because there's a circular room in it, they talk about it being 3, because that was a good approximation if you went to build it. And the architects at the time worked really, really hard on getting good approximations to pi so that they could build things properly. So what we can do is we can look at a way of calculating the circumference, or how much material we need on a circle. So let's say I have a circle, and I know that its radius is 4 inches. So I have a 4-inch radius. So if I were to take some string to go around the outside of that circle, knowing the radius is 4 inches, I would have to calculate its circumference. And so I'm going to have 2 times pi times 4. Now what I do when working with these is, if these multiplications are nice numbers, as the 2 will be, if the radius is nice, I'll multiply them first. So I'll say this is 8 times pi. And then I can use the approximation for pi to multiply my decimal. I'm going to have 2 decimal places in this particular answer. So 8 times 4 is 2, carry my 3. 8 times 1 plus the 3 is 11, carry my 1. 8 times 3 is 24, plus the 1 is 25, and 2 decimal places. And this is in inches. And so approximately, and we'll use a squiggly line for approximately, the circumference is 25 and 12/100ths of an inch for a circle that's 4 inches in radius. All right, so this is multiplying decimals. We will continue our exploration of decimals in the next video.